So now what I can do, right, is enhance the single cycle processor to handle I type instructions. You know, you can add I, and I, or I, and things, right? So this is similar to R type, but the second source comes from immediate. All you have to do is you have to change the ALU source to select the immediate and IMM source to pick the correct immediate. Okay, so that's why if you look at it here in the R type, we said that this was a don't care, but now for I type, of course I have to choose, you know, what this immediate data is, right? And I have to choose 0 0 because I am doing it in the I type instruction. Okay, my only the ALU operation is changing. Instead of addition, we are going to do ANDing, this, that, and all that, right? And therefore, I am going to say immediate source is going to be 0 0. That means the last 20 to 31, those 12 bits are going to be chosen for the immediate data and then sign extended, right? My ALU source, what is my ALU source now? It has to be 1, remember, because for the I type instruction, I need my data to come from the immediate and not the thing, register, right? Likewise, other things are essentially the same. Register write has to be 1 because you are trying to do there is a destination register that is needed to be written into, right? So it is always operation RD, RS1, IMM, right? That's how the instruction is, right? There is no memwrite, so it is 0. Result source is 0. Why? Because I am not doing any memory operation here. So when you are not doing memory write or memory read, then these two will be 0 essentially. Okay. Of course, you are not doing a branch, and therefore my ALU operation is going to be some 1 0, right? So that I can do an AND I, right? Essentially, that's what. So if you look at the difference between the R type and I type instruction for the same AND operation, we said AND x6, x5, x4. Now we are saying AND I x6, x4, some immediate data. The only difference really is in this guy and it is in this ALU source, right? Everything else remains the same. Okay. So the AND I that you see here, like I told you, you are essentially going to, of course, write something back into the register. My immediate source is 0 0, and you are now exercising this path of the mux because you want the second operand to be the immediate data, and then you are bypassing this memory completely, getting the data back into my WD3, right? Yeah. Now we can also extend this functionality to handle jump and link, JAL, right? So what is this? This is very similar to the branch and equal, right? But the jump is always taken. So in some sense we are saying this is like the branch on equal x4, x4, label, right? Where you are always branching because you are giving the same arguments. But now here we are saying jump and link, which is just unconditional branch, okay? So which means that the PC source should obviously be 1, okay? Immediate format is different, and therefore, we need a new immediate source. So what happens here is that the way the immediate data is interpreted in my opcode is going to be different. And therefore, earlier we had immediate source 0 0 0 1 1 0. Now we need a fourth type because this new instruction has a different encoding format for the immediate data, right? However, remember, apart from this whole thing, right, what we want is the jump and link must also compute PC plus 4 and store in RD. Now what is this jump and link? It's effectively like the call instruction that we did in x86. Okay, and I told you in this pseudo instruction, this call was mapped to this jump and link. So there is a destination register that is being operated on here, and that is my return address, RA. Okay, and PC plus 4 is where we want to return to. Okay, so that is very important out here. So if you look at this, I want to do jump and link, right? We basically want to give some sort of a thing. So let's look at the, right? So yeah, so basically we have just a destination register, right? And we have the thing, right? So we want to do jump and link, return address something here. So this is where, let's say 0x1000, 0x1004 is where, let's say I have another add x1, x2, x3. Okay, so this is like saying call, okay, RA comma label. So I want to basically take that label, put it into PC, and the next instruction is at this, right? So PC plus 4 has to be calculated but put into the register return address. Okay, that's the most important thing to remember here. So what we are going to do here is compute PC plus 4, store it in RD, right? And then we are going to take the jump branch. Okay, so here the main decoder, what we are going to do is we are going to add one more signal called jump. Okay, because this is a new instruction, this needs to do something slightly different from the branch and equal. Remember, the branch and equal just was like the jump instruction in x86, so where we didn't have to worry about return address and all that. Whereas the jump and link of RISC-V is like the call. So additionally we need to worry about where it has to come back, and that state needs to be stored. That's why we have this JUMP, which is a new control signal, right? Other signals are still very similar, right? Now the immediate data, remember, you look at the I type instruction, B type instruction, S type instruction, the encoding of this immediate data is very different, right? So basically, we have 12 bits in one case, 12 bits in most cases, whereas in the jump type we have 20 bits. Okay, so bits 12 onwards really is sort of my 20 bits of information that I have, right? And therefore I need this IMM source to have a fourth type 11, right, to handle this J type of instruction, right? Therefore, if you look at this jump and link, what we have is my reg write has to be 1. Why is reg write 1? Because I am calculating PC plus 4 and putting it into my return address, which is one of the registers in the register file. Okay, the IMM source has to be 11 because it's a new type of immediate encoding that we need to worry about. The ALU source really does not matter. Okay, why? Because the ALU is not being used in this instruction. You need to do PC plus 4, but for that there is a separate adder. Okay, and therefore the ALU source does not matter here, right? Mem write obviously has to be 0 because I don't want to do memory write, right? The result source, again, what is this result source? It is going to be 10, branch is 0. Okay, why branch is 0? Because really I am not doing any traditional branching operation. So we'll come to this. And the ALU operation also does not matter. We have now introduced a new control signal called jump, which is different from branch. Okay, that's why if you see branch is 0 but jump is 1, and in the other cases jump was this thing. Okay, so only in the branch and equal, branch control signal is 1, jump is 0 there. Okay, so we look at this whole thing now. Okay, so this is how the control signals are shown. What we are basically saying is, my PC plus 4 it has to be evaluated because the return address, that's where I want to come and I want to write it to that register. So that's why you see this PC plus 4 now is going as a third input to that multiplexer there. Okay, remember this multiplexer. By the way, each of these multiplexers is like a multi-bit multiplexer. Okay, in this case it's a 32-bit multiplexer, right? So you get PC plus 4 and that is going to the thing. So this is what is going to go into your destination register. Okay, now what are you going to do? You are going to take my destination register 11,7 here, right? My A3 has to be address 3 is going to be treated as the destination register, and then you are going to do a reg write, of course, but most importantly this result source, which was earlier just 1 bit, has now become 2 bits because I need a 3 input multiplexer now and not a 2 input multiplexer. So earlier we were selecting between memory output and ALU output. Now I need to select between memory output, ALU output and also the PC next, the PC plus 4, right? So that's why that is a 2-bit number now, right? And result source has therefore become some 1 0. So earlier it was 0 1, now we made it 0 0 0 1 1 0. Okay. And of course, apart from that, my register write is going to be 1 because I need to write that data back into my into the destination register, which is PC plus 4. And then what we are going to do now is, based on my jump, right, I am going to essentially determine what the PC next is going to be, right? So the PC source is obviously going to be some 1 here. So now what you see is, you have taken this immediate data, pass it through the sign extender, and that is being controlled by this IMM source 1 0, and in the jump instruction it is now equal to 1 1, right? That comes into the sign extender, that gets extended, and then you add it to the PC, current PC value, you add it, and that is now fetched. It is going back to another multiplexer like this, which is controlled by this PC source out here. Okay, so this was 0 and 1. So it is more a case of where this whole next instruction has to reside. Okay, so having discussed the architecture and implementation of the RISC-V processor, let us look at the program execution time. Okay, so like I said, it's a number of instructions cycles per second, right? So if you look at this whole thing out here, in 1 clock cycle we are executing 1 instruction at a time. So whatever instruction it is, it executes in 1 clock cycle, and therefore all we have to do is the program execution time, right? Program execution time, right, is basically number of instructions, right, into cycles per instruction. How many cycles you are taking per instruction? In single cycle processor it's 1, right, into the clock period, into the clock period, right? So therefore so what really matters now is, in order to understand the program execution time, we need to go back and look at this expression. Okay, so it turns out CPI is equal to 1 for a single cycle processor for any instruction, right? So therefore, if I give you a bunch of instructions, it's just the number of instructions into the clock period. Okay, so you take x86, you compile the code, you get a bunch of instructions. Like I told you, the x86 will most likely produce a code snippet, assembly code snippet or a machine code snippet, which is smaller than that of the RISC. Fewer instructions compared to RISC. Okay. But if you were to implement both x86 and RISC in single cycle as a single cycle processor, right, it could be still much slower than the RISC-V. Even though the number of instructions is smaller, the reason for that is the clock period is going to be much smaller for the risk 5, and we will see why that is the case.